Right, good morning. In today's lecture we will see the Poisson distribution. Poisson distribution. So in the previous classes we have seen one of the discrete probability distributions, which is binomial distribution. Let me give a brief note on this binomial distribution. Binomial distribution, in which there should be n trials of the experiment. N trials should be independent ones, and in each and every trial there should be only two outcomes of the experiment, namely success and failure, and the probability of the success is same for each and every trial. Then we treat these trials as Bernoulli's trials, and which plays a role in binomial distribution. But coming to this Poisson distribution, this is, we can say, a limiting case of binomial distribution only. So what are the limits that we need to consider to obtain this Poisson distribution? See, as in case of binomial distribution, there should be n trials of the experiment, n independent trials, but this n should be large. I can say n tends to infinity. This is a limiting form to obtain this Poisson distribution, and the probability of success P is very close to 0, a very small number. With these limits, the binomial distribution is Poisson distribution only. So I can say Poisson distribution is approximation to the binomial distribution. We'll see how it works. We have binomial distribution formula. It's NCX P powered x Q powered n minus x. As we all know, n is independent number of trials, x is number of success, P is probability of success in a single trial, whereas Q is probability of failure in a single trial of the experiment. Now we just expand this, like what NCX is, that's what I am writing. It's n factorial over x factorial times n minus x factorial. P powered x Q powered n minus x. Just NCX is this thing. Now let me write this n factorial as n into n minus 1 into n minus 2 into and so on, n minus x minus 1 into n minus x factorial. The same can be taken in this way, over x factorial into n minus x factorial, and this is same like p powered x q powered n minus x. Here one more assumption is there with us. The assumption is that the product of these two, as n is tending to infinity and p is tending to 0, the other thing is that the product of these two is a constant. Let us suppose say lambda. This is also one of the other limitation will take in this approximation. So instead of p, I could take lambda by n. It has come from this third limitation, lambda by n. And since q is 1 minus p, we write this as 1 minus lambda by n whole power n minus x. So this is there with us. Now these cancels, and see, in all these factors I would like to take n as common, so it becomes n powered x, because there will be x many times of n in all these products, so that n powered x, and 1 minus 1 over x, it becomes 1 over n, and this becomes 1 minus 2 over n, and so on, 1 minus x minus 1 over n over x factorial, and this is lambda power x over n powered x, and this is 1 minus lambda by n whole powered n minus x. This is that what we are having. Now these two cancels, and as per our consideration, like n is tending to infinity and p is tending to 0, the function is becoming 1 minus 1 over infinity, which becomes 0, like it becomes 1 and this also becomes 1 and this also becomes 1, because something by infinity will approach to 1. So, the numerator completely is becoming 1 over n factorial, and here we are having lambda to the power x, and this can be 1 minus lambda by n powered x powered n over 1 minus lambda by n powered x I can write. Since it is minus x, I can write it in the denominator. As this numerator, as n is tending to infinity, becomes e powered minus lambda, and since it is power x, this part will become 0, so that it becomes 1 minus 0, like 1 powered x, which would be 1. So that rule I am applying here. The function is now will become 1 over x factorial lambda powered x, and this, as I have already told you, e powered minus lambda over 1. Now the function has come like this: e powered minus lambda powered x over x factorial. So this is as x is running from 0, 1, 2, so on, and as n is large, as I have told you already. This is treated as a probability mass function in case of Poisson distribution. See, a random variable x is said to have Poisson distribution whenever its probability mass function is given by fx is equals to e powered minus lambda into lambda powered x over x factorial. But this is been taken whenever n is a large amount, whereas the probability of success is very small, and n into p, product of these two, is a constant, not 0 or not infinity. In this case, we treat it as Poisson distribution. Clear? So today in this lecture we have seen like Poisson distribution is approximation to this binomial distribution with these postulates, with these rules. Thank you.